They're smaller than a fingernail, almost invisible, yet microchips are the engines behind modern life, and this is how they're made. We're talking atomic precision, global power, and engineering bordering on magic. Every one of these microchips begins with one of Earth's most abundant materials, sand. But not just any sand, only ultra-pure quartz, refined into 99.99% pure silicon, makes the cut. Through a process called the Czochralski method, this raw material is transformed into massive monocrystalline silicon ingots. Some stretch over 6 feet long. These ingots are sliced into paper-thin wafers with diamond-edged saws, each destined to become the foundation of millions of transistors. But why silicon, you ask? Its atomic structure makes it the perfect semiconductor, allowing it to both conduct and insulate electricity with incredible control. But this is more than chemistry. It's digital destiny. From a handful of sand comes the beating heart of all our data and our daily lives. The irony is haunting. The most advanced technology on Earth begins in Earth's dirt. But it's not what silicon is. It's what we teach it to do that changes the world. And here's how it all starts. The journey of a chip begins specifically with a silicon wafer. This is ultra-thin, mirror-smooth, and pure to an atomic level. These wafers are precision-sliced from massive cylindrical ingots, just 0.75 millimeters thick. Each slice must be flawless. One microscopic defect, and the entire wafer is as good as junk. After slicing, each wafer undergoes a polishing process so exact that the surface variation is less than the width of a DNA strand. Why? Because modern chips demand perfection at the nanoscale. I mean, even a dust particle could corrupt a circuit. Next, the wafer is cleaned using high-purity chemicals and plasma treatments. This leaves behind a pristine surface, ready to carry the world's next set of instructions. It may look like a lifeless disk of glass, but this wafer is about to become the digital canvas for billions of microscopic structures. Every breakthrough starts right here, on this sliver of silicon. Here's where light becomes the architect of machine intelligence. This is where science fiction meets brutal precision. Photolithography, the process of writing electrical blueprints with beams of ultraviolet light. It begins by coating the wafer in a light-sensitive film called photoresist, a material so sensitive that even ambient particles are kept at bay in ultra-clean rooms 10,000 times cleaner than a hospital OR. Next, extreme ultraviolet or EUV light, focused through a complex lens system. It projects a pattern onto the photoresist using a reticle, an intricate glass mask that holds the design of microscopic circuits. This light etches a molecular map that will become transistors, memory gates, and the logic systems. The exposed areas are chemically developed. Then the wafer is etched with plasma or ions to engrave the pattern into its surface. But this is just one layer. Some chips require over 100 layers, each aligned with atomic perfection. This is not printing. This is engraving thought. Burning logic into matter using beams of light, if you will. Now the circuits need to connect. Once these transistors are carved into silicon, they still can't do anything. That's because they're isolated. And this is where metallization steps in. This is the step that basically brings the chip to life, foraging electrical highways between billions of tiny components. A layer of copper or aluminum is deposited across the wafer using chemical vapor deposition or sputtering, forming the base of the chip's nervous system. But the connections aren't just sprayed on, they're patterned using photolithography again. Then they're etched, forming precise channels and contact points. Each layer is separated by ultra-thin insulating films, and chips may have dozens of metal layers, stacked like a microscopic skyscraper. Engineers even use tungsten vias, vertical shafts that connect one layer to the next, like elevator shafts for electrons. This is where isolated logic becomes a symphony, circuits communicating, power surging, and intelligence flowing through pathways finer than a blood vessel. The brain of the machine is alive. This next step, perfection or total failure. The wafer is now complete, but it's not ready to celebrate. First, it must prove itself. Each wafer holds hundreds of chips, but not all will survive. Using automated test equipment, electrical probes touch down on each chip, firing signals and measuring responses. A single misfire, instant failure. In this world, there's no room for almost. This is where heartbreak happens. Months of precision discarded if even one layer is misaligned. Only the flawless make it through. Once testing is done, lasers map out the good chips. Then comes slicing. This is called dicing. The wafer is cut into individual microchips using diamond saws or lasers, each smaller than a fingernail, yet ready to power entire worlds. The tiny squares, now separated, are picked, sorted, and prepared for packaging. This stage is all about precision. It's not about potential. Billions of calculations demand nothing less. In this factory, if a chip fails to switch on, responds too slowly, or even consumes too much power, it's out. No mercy, no maybes. Now the brain needs its armor. Each microchip is now a delicate powerhouse, capable of extraordinary computation but fragile as a heartbeat. Enter the final line of defense: packaging. This is more than just a plastic case. It's nothing short of a life support system. First, the bare chip is mounted onto a substrate, which kind of acts like a motherboard's miniaturized cousin. Tiny gold or copper wires, thinner than a strand of hair, connect the chip's internal pads to the substrate's circuits. This process is called wire bonding or flip chip attachment. Next, it's encased in an epoxy resin or ceramic shell, designed not only to protect against dust and moisture, but also to dissipate heat and block electromagnetic interference. Some packages even include built-in heat sinks or shields to guard against radiation. That comes in handy for chips used in satellites and medical implants. This step is survival. Without protection, even the smartest silicon dies young. With it, that chip can run your phone or steer a Mars rover if it must. Now all this genius must meet the world. From pristine clean rooms to the chaos of Earth, the journey is complete. These chips, some no bigger than a thumb pin, are now packed by the millions and shipped across continents. They vanish into everything: phones, cars, planes, satellites, pacemakers, military drones, Mars rovers. Global tech giants from Apple to Tesla depend on this flow. The tiniest chip may hold billions of transistors, performing trillions of operations per second. Yet look at it travel so quietly, anonymously, inside every device that defines modern life. Supply chains stretch across borders and oceans, from fabrication plants in Taiwan and the US to assembly lines in Malaysia, South Korea, and beyond. A delay in one factory, entire industries stall. This is the moment silicon stops being material and becomes reality. The unseen engine behind every beep and breakthrough of the modern world. Just chips? More like the pulse of civilization. This whole process isn't just manufacturing, it's a global war. Behind every microchip is a geopolitical knife fight. These tiny silicon wafers are no longer just technology. They're power, control, and in some cases, national security. The most advanced chips are built using machinery from the Netherlands, with designs from the US. They're fabricated in Taiwan and assembled in Southeast Asia. A disruption at any point, the world's tech grinds to a halt. That's why countries are racing to build domestic chip industries. The US launched the CHIPS Act with $52 billion in subsidies. China is pouring hundreds of billions into catching up. Tensions around Taiwan, home of TSMC, the world's most advanced chip maker, aren't just political. They're about who controls the future. This means it's not about phones or cars. Think AI, military systems, space tech, and literally the global economy. You could say microchips are the new oil. Whoever controls them controls civilization's most powerful tools. These chips might be micro, sure, but they decide who leads and who gets left behind.